Hey everybody, welcome back to Knife Making Tuesdays. Super excited to be working on our new knife, the Integral. In this video, so we're gonna work on the blade. So the blade is one of the most complicated things we make. There's a lot of processes involved in a blade because you gotta water jet it, you gotta surface grind it, you gotta soft mill it, you gotta heat treat it, you gotta lap it or grind it, you gotta mill the bevels in, grind the bevels, polish, finish. There's just a lot of steps to make a blade a really good blade. And I'm going to start taking you guys through the process. So we're going to jump into Fusion 360, my design software of choice. I'm going to show you how we're designing the fixture, how we're going to clamp it, how we're going to hold it, and go into the tool paths of making not only the fixture itself, but also the blade itself. And then we're going to jump on the Speedio, we're going to make the blade, and then if we have time, we're going to go to heat treat and get the guys to heat treat it for us. So let's jump right in to Fusion. Here we go, Fusion 360, baby. Because we have standardized to these Iroha bases, there's normally a pull stud that goes here, but I use this little cylinder because this circle is my X0, Y0. The pads are my Z0, and then these little square alignments are my XY rotational alignment. These bases are awesome. And this is a 72 millimeter pallet that we have basically milled dovetails into there and machined and milled these clamps to hold on to the dovetails. And this kind of rectangular fixture is how we do our rasp blades, and it's been awesome. So we use the same technology for integral blade. I also have these two screws holding it down through the fixture into the pallet for like triple extra security, just because we're hard milling on the sides doing the bevels, and it's fairly easy to add those screws. So what are we looking at here? We're looking at the integral blade shape milled out of the top of the fixture. Top of the fixture is decked super duper flat. Let's see, blade and water jet stock. Water jet stock. Okay. So here is our blade shape. How it sits, but it can't just sit there, it can't just float in space, right? You have to be able to hold it down somehow. So how do we hold it down? Same way we hold down our rasks. In fact, we will start out using a rask blade because we have hundreds of them in stock, already surface ground. Well, a handful of them already surface ground, but as opposed to, you know, we don't do water jet here in-house because it's the one job I never want to do. I don't want to buy a $150,000 water jet, and it's messy and it needs all kinds of maintenance. Gross. I'll let other people do it. We've got a shop 5 miles down the street that does amazing work. One of the very few processes we don't do in-house is water jet. And what that is briefly, it's basically 50,000 PSI, maybe more, super high pressure water and sand that blasts down like a garden hose, but times a billion. And cuts out a profile, whatever you want. Tolerance is quite good, and surface finish is usually decent. So we have this rask water jet shape. I have lots of them, right? We bolt it down on two ends, and then eventually the front tab gets cut off and the back tab gets cut off, and you're left with a blade. Now, not only that, where is my clamp? We also put a top clamp on it, like so. So this clamp bolts down from the top, has a cantilever in the back, tilts forward, and holds the blade still so that when we do cut off the tabs, the blade is still held in place. Very important. You know, as much as other parts that we've already made can be used on this new project, the better for us because it's less development time. This clamp may look simple, but it takes time to develop, to make, to machine, to, you know, make sure it's got all the clearances it needs for everything. So if I can use that, win, and I can. Even though this blade is quite a bit smaller than a rask blade, I was able to shift it over a little bit and make it fit just fine. So notice how on this side here I have two screws. I have one to hold the rask blade shape, and then once we do eventually get a run of water jet blades for this integral, if I can use the same fixture, even better. So integral water jet blade. So this one is what the integral shape, you know, ideal net shape might be. Usually I add about 50 thousandths of an inch around the outside of the part, depending, but that gives you enough meat to machine off. You know, water jet has some tolerance issues, the screws have some tolerance issues, etc. So 50 thou gives you enough meat to dig into and be fine. So the first step is actually to start with a water jet blade, not that one, and chop off all the extra junk, because ideally I want my integral blade machining program to just be set it and forget it, just run it. So let's blank out a bunch of Rask blanks to become an integral blank. Let's see here. I have two files open, if you notice that. I have integral blade cam and integral fixture CAD and cam, where I'm actually designing the fixture. You know, the design tree at the bottom here has all the steps that took from copying this fixture from the Rask and defeaturing it and adding new holes and new features and things like that. So this is my sketch that compares basically a Rask blade to an integral blade. And then I'm basically following this line with the tool to chop off the bottom. Not too worried about the top. So moving over to the CAM side of Fusion 360, the manufacturing side they call it, you got design, generative, animation, manufacturing. Design and manufacture are all I use. I have a setup folder here, I can highlight that, with 4 operations in it, using a, what tool am I using? Using a 3/16 4-flute end mill. It is tracing down. Now, because I don't want to wear out the tool and I don't want to just hog through the material, for now anyway, I figured I would just do little 10 thou passes going down, use the radius of the tool. This tool is later used for profiling and finishing the walls of the blade, like the side walls. And if I only wear out the bottom 10 thou, it's not going to affect future production. So it's like getting 2 tools out of one, basically. And it takes a minute 37, whatever. Not fast, not slow, I don't care. If we do a quick simulation of that, zip, zip, zip. Obviously, I can't put the screw hole in here yet because there's no hole, so that wouldn't normally be there. But yeah, here you can see what's going on. It is chop, 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 chop. Okay, so that's the first one. Now I go here and bore the screw hole. Like I said, this model will not be there. If I click on it, it should highlight. Yeah, it underlines this. So I can go in here and I can hide that screw. So now when I go bore screw hole, I'm just using a 2D bore toolpath, zip, 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 zip. Nice and gentle, nice and easy. Easy peasy. Now I go in with a slightly smaller tool because I want to, you know, gently have this flap fly away. So this is a 3/32 flat end mill, and then I come in with an 1/8 inch high feed end mill and I zip off this tab, leaving a little bit 10 thou on the floor or something like that. And this one's using a zigzag toolpath, which I find high feed end mills don't care. They love that. Zip, 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 zip. Add the shaft in there. Sweet. And hopefully that is thin enough that it can just break off and not be a huge problem. Or when I put the screw in, I can actually finish that surface. We'll see. So anyway, that's the first step, is making a water jet blank. Okay, going back to the fixture, this other file, I want to go into a couple little details about how and why we're doing what we're doing. Okay, so you understand the water jet blank is clamped down with 2 screws and then a top clamp, like so. Okay, you may be wondering, why is it so deep around the outside of the blade? What is the benefit, the purpose of that? For one, it's to get the tool below the blade. Sometimes, if I can get away with it, I use a ball end mill to do side profiling, but the ball radius has to go below the part. So you need enough fixture clearance to be able to do that. Why would you do that? Usually use a ball for the ball itself, not for the sidewalls. And these side flutes are completely underutilized. So if I can get dual use out of a tool, especially on the Speedio that only has 21 capable tools to fit inside of it, huge win. So I'll often do that with an 1/8 inch ball, a 1/4 inch ball, something like that. And I need to be able to sink that tool below the part to be able to use the straight sidewalls that almost never get used. I'm not necessarily doing that in this case, but I am doing it on the inside, on the pivot. I do it on the Rask quite a bit. So it's nice to be able to build a fixture with that in mind. Also, chip management and coolant flow evacuation of chips is hugely on my mind, because imagine when you're cutting a chip, where does it go? Okay, does it get stuck inside your hole? And then you're expecting the coolant to blast it out, but meanwhile the tool is cutting another chip and another chip and another chip. And is it cutting the previous chip? Is it cutting the chip that's just floating around? Is it recutting a chip? It's a real problem. So it's a thing. So what I like to do is, let's hide this blade. I can hide it like that. What I like to do is clearance my fixture in a way that has chip flow in mind, yet still enough support to hold the blade. So I've got all these pads that are going to support any kind of vertical load and keep the blade nice and stiff and still. But as chips are being introduced through the hole, they have an exit. They have 3 exits. As we're cutting this slot, chips can disappear. They can go out. They will not get recut. These are very small tools, you know, 16th inch kind of thing, even smaller sometimes. And we don't want the chips to get in the way. So that's what I like to do there. Also have enough clearance to cut off the tab in the front and just to wash the chips away. I had to cheat a little bit here with this post because the screw can't go much lower for a couple of reasons. So I wish I could have sunk that lower, but to keep it the same as the Rask, I wasn't able to. Whatever, that's fine. So if we go into the cam of making the fixture, we've got a bunch of ops here. I basically start out with this blank like so, that same thing we use on the Rask, and then I do this on the Kern. So I'm able to 5-axis tilt this thing. Da-da-da-da-da, da-da-da, drill the holes, start adapting these features, finish a couple features, yada, yada, yada. Use a small high-feed end mill to come down and zip, 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 zip. Face it real nice, chamfer all the stuff, you know the drill. Sometimes I'll use a long through coolant drill bit to clear out the bottom of a hole to flush any chips out of it. So that worked really well. But 40 minutes to do that, most of which is spent, you know, slowly facing. 7 minutes to do this facing toolpath. I don't really care. It looks really good. So if we go back now onto the blade machining side, so we've done our water jet blade. Now, what's it going to take to make this blade? What's really cool, see these little radio activate buttons? If you set up your setup properly with fixture, model, stock, etc., then as you jump between different setups and you click your radio, everything changes accordingly. So for the roughing, I have a Rask stock. You can see the light, whatever color that is, as the water jet stock. And then I slip to here, and now I have my integral stock and my blade model and all the clamps and everything. So quite a few operations to do an integral soft blade the way that we do it. And you can start to see how every toolpath is coming in and wants to do it, right? Start by spotting. Spot the jimping holes. I like to drill these holes and ream them if I can, because it leaves a really, really nice finish. Drilling with a 059 drill bit, less than 1/16 of an inch, through coolant, and then I ream those 2 holes, drill some more clearance holes so that the tool can plunge into the bore. Now I use a, what is this, a 1/16 high feed end mill that we had custom made from DeBoer. Zip, 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 zip. Works awesome. Here's an example where I do use a ball end mill and I plunge it through the drilled hole, through the part pretty deep. You can see it goes all the way down, and then I'm using the side flutes to de-adaptive that hole. Works awesome. Then I semi-finish it, bore it to size, using dedicated tools. So this here is some of the features for the button lock. Now, this is all theoretical. I don't know if this is going to work, but in my head, that feature and also this little taper here, 3-degree taper, are what's going to, this is going to lock it in place in the open position, and this is going to be our detent. The button is going to pop into that feature and then hopefully pop out of it in a nice controlled flick manner. I like to do a version engraving, V1.0, And then I'll do V1.1, 1.2, so that as we make tweaks and modifications, it follows the blade through production. Bunch of little chamfer stuff, start to rough the outside profile. This feature is kind of small. I have to come in with a smaller tool and finish that. Here's where I cut the first tab off. You can see the tab is there, and then the tab is not there. A lot of times I will use actual sketches to define that. Like this is my soft blade cam sketch. So I'm creating this kind of arc that toolpath is going to go into. And then I can chop that tab off, because the last thing I want is for the blade to move. I do not want the blade to move. So if I can gently hit it from different ways, then I can, you know, only benefit. And then I do come in and I use, again, that 1/8 inch ball, and I clean the burr off of this front tab that we broke off earlier. So, I mean, in a nutshell, that's kind of how we do that. And then in the future, we're going to put our serial number engraving on the spine here, and the name of the knife. I got some good ideas for the name of the knife. Actually, I'm pretty sure I locked in on one. We'll save that for a future episode. But because this engraving would have to be not a 3-axis, but a, well, 4-axis really engraving, coming in, tilt the fixture, come in from the side, I'm going to plan to do that feature on the kern so that the blade can pallet change out of here into the Aroa and then pallet change into the kern, and the kern can do this 1-minute operation where it tilts it and engraves the spine. Lastly, the other thing that I really enjoy about these fixtures is it's kind of a one-piece flow fixture where we can use the sides of the fixture to hold a blade to machine the cutting bevels. Like, I don't have a rasp on me. This is the cutting bevel. So for the Norseman, we slap it straight up and down onto the side of a fixture, and we use a ball end mill about the size of my finger, and we come in and we 3D. That's how we get those machine lines in the Norseman. In the rasp, what we do is we actually tilt the blade on the fixture at a 4-degree angle, like you can see here on the screen. 4-degree angle, so that the exposed cutting edge is vertical, straight up and down to the world, so it can be ground on a 3-axis machine. That's how we do the rasp. It's been awesome. I want to apply the same technology here to the integral. These features are still rasp features, so one of my to-dos for the next week is to kind of defeature this and apply it to the integral blade. And then here we have a Delrin insert that kind of supports the already machined second side of the blade, so it doesn't chatter, vibrate, whatever. And we machine that into place so that it supports the blade. So I'm going to worry about grinding the blades later, but now that I've shown you, the dozen hours of design and cam just in the fixturing and the programming to make this blade, let's go to the machine, let's go to the Speedio, and let's see if it works. Let's see if there's any issues. I'm pretty confident that I did everything right, but I'm still going to walk my way through it. Luckily, I got the cycle time down to 7 minutes, 47 seconds, according to Fusion. And I'm really, really happy with that. That's flying for all these little details. Yeah, let's go to the machine, see what we get. We are cutting an integral soft blade. So exciting. Fast tool change. I think right now it's cutting the tab off. It's hard to see anything. But yeah, it's happening. And now it's coming in and putting in a little micro chamfer on the top and the bottom edge of the blade using a thread mill. If we can get away with it, we only like to machine the blade just on one side. We don't need to flip it over if we don't need to. It adds in a whole nother step, and it's mostly unnecessary. All right, it's almost done. One more cut. Done. Done, 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 done. Look at that. It's Looking good. See if we can get the pallet changer going. Yes. Focus. So it's grabbing the pallet. I'll look through the center here. Putting it back on the other side of the Aroa. Going over to 67. Grabbing 67. Rotating and coming right back in here. Sets it down. Retracts. Closes the door. And we're back to running this part. It's working. So I was here late last night, like really late, finalizing the pallet change sequence macro and how we schedule all that. Finally got it going great, so now we're starting to sequentially schedule part to part to part to pallet to pallet to pallet. And also got the soft blade done. It's coming together, man. It's really, really coming together. Also, real quick, check this out. So I tasked Eric with 3D printing a tool tag system. So each of these tags, tool 35, is in spot number 15. Bunch of dual color 3D prints. Tool 32 is in spot number 12. Tool 11's in 11, 31's in 10. Blue for soft blades, which we just did. Red for hard blade grinding. Green is for fixturing tools. Gray is for always tools, like my fan and my probe are always in the machine. And then not only that, but the blue corresponds to a blue storage rack, or a white storage rack, or a black storage rack, or green for fixturing tools, or orange for lock bar inserts, black for carbon fiber. So this turned out really, really good. So now I can have pre-staged tools stored in location. These are all my carbon fiber cutting end mills. They have numbers, specific numbers that never change, so I can take them out, put them back in, put them in the machine, whatever. These are my fixturing tools, like a 3/8 beater end mill is tool 49, drill, tool 61, thread mills, etc., etc. So we're moving into this system. Last night this was completely full of tools, but I've now put them all in the machine to make soft blades, and we've got all the blue ones there. So actually, I just realized this, even from a distance, from like my desk over here, I can look and I can see mostly blue is loaded in the machine, so I know it's loaded for soft blades, which is really cool. And now we are grinding hard blades. So we're taking a rask blade that's already been heat treated, lapped, soft milled, you know, really nice looking, and we're grinding the cutting bevel into it in a hardened state. And that requires tool 1 for roughing, tool 19 for grinding, and tool 5 to chop the tab off at the end. So only 3 tools to grind blades, so we can always leave those and then still have a bunch of tools for other stuff. Going around to the back of the machine. So you got the Kern over here, you got the Speedy over here, a row in the middle. Our blade pallet is in number 65. So I'm going to go over to the Kern and I'm going to call my engraving program. So, temp, integral, John, program 1001 in pallet 65. And it's going to call the file 1001.h that's in the folder integral. And this should work. So it's got to put this pallet away. Let's try it. Okay, opening the door. It's going to have to do a gripper change first, because not only was it facing towards the Speedio, but it's got the wrong gripper in. So what's cool is it's got these 2 grippers, and it's like changing a hand basically. It's going from a small hand to a big hand, and it does this automatically because it knows. So that whole gripper gets unclamped. All right, so it's going to put this guy away wherever it was, 20. And then it's going to go back and it's going to change to the small gripper again.
Nope, something's wrong. I think it's just calling the wrong schedule. Yep. So my schedule happened, even though I have them both as an order, number 1, even though they're both status 1 and order 1, this top one wins because it's a lower cell number, 10 instead of 122. So I slightly goofed there, that's fine. So I need to make this order a 2 so that this one wins. So I'll do that. Let's try this again, shall we? Now it's going to put away pallet 10. It's going to go do that gripper change again. Lift up, should be grabbing my pallet right there. Excellent. Coming over here. Put it in like a boss. Good. Perfect timing. Now I don't have to be the only one filming. I think his spidey senses were tingling. Okay, we're gonna call up the engraving tool, hard engraving tool, soft engraving tool. Same tool, different purpose. Spin, all right, I'm gonna let Ryan film this one. Okay, so we have the pallet tilted 90 degrees. Spindle spinning at 30,000 RPM. I'm fairly confident that this is going to do what I want, but wait. Yeah. All right, it's engraving. It's good. It's like based on the Rask engraving that we do. So I've done this before, but still a new setup, new palette, new program, new blade. I only trust myself so much. Get some water on there. Yeah, it's going good. For this prototype, I'm engraving quite a lot of words on it. So the side of the tool is getting awfully close to that fixture, but it should be fine. It'll self-clearance if it needs to. All right. Looks good. So at this point, I've made 2 soft blades, put one together in the knife. It goes together great. The pivot size was perfect. We didn't have to barrel lap it bigger. A couple of the chamfer tools and corner rounding tools undercut a little bit. So on the second blade, it raised it by 1 thou or 2 thou or something. There's always fine tuning there, but once you get it dialed, it holds pretty good. But I put it in the blade. It's kind of sweet that because of the shape of the blade, it's actually able to close even with the tab in place. I was joking with the guys that it's a lanyard, but no, that'll get cut off. So it'll be flush to here, and then get slightly under flush so that you don't cut yourself. So the blade will be under the radius there. But yeah, seeing this thing, feeling it together, feels really good. It is a small knife. No doubt about it, but that's what I want right now. I want to make a small knife. I like it, man. I think it's gonna be sick. So the next step for these 2 blades is send them to Sky for heat treat, and then probably he'll heat treat them tomorrow morning. And then things like how this looks really big, it's because there's a lot of extra meat here. Once we grind the bevels into it, then there's still about 50 thou left here that has to be cut off. So this thickness right there will be about half on the finished blade. And then we'll chop off the tab and the guys will blend it nice. Yes, 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 yes. And then work on the button and the stop pins. And then I still have to, I have the bevels designed, but I don't have the fixture made or designed or the clamps or the program yet for that. So that'll be the next big, big challenge. I like it. All right, heat treat time. We got Sky here doing the heat treat oven, and we have the 2 integral blades in the oven right now.
And some rasks.
And some rasks, so we're pulling it out.
I gotta figure out, these are small.
New process, new blades.
And I probably want to go a little lighter on them.
So these are the water-cooled quench plates that we've shown in previous videos, going to an aquarium chiller.
They are so much better than the old ones.
That's 71 degrees. It'll rise by a little bit, right?
Yeah, it varies. It runs like a kind of like a refrigerator.
Okay. So we're all that red hot heat, we're sucking it out relatively as quickly as possible.
Those mostly flat enough. Here goes the other one. So
beauty. And can you explain why you want that heat out of there quickly?
So the metal is a near liquid state, and the actual crystals that make up the metal are flowing a little bit, and you want to lock them into a specific orientation.
Okay.
This is like pretty layman's terms.
Sure,
You're
yeah.
locking them into a specific orientation where it stays nice and hard. If you let it cool down on its own, it wouldn't harden up, and it wouldn't be a good knife blade at all. Keep going with these rasks. Even compared to a rask blade, because they're going to be shorter quite a bit once the tab's cut off, right?
Yeah, quite a bit. So the tab will eventually be cut off, but we leave it on for now for hard milling fixturing to be able to clamp it, and a bit more meat for heat treat to be able to keep it flat.
Something funny that I'll go into this more when I open them up, but because of the way the tab is, and because of where the top stop pin location is,
Okay.
it almost looks like it's a front flipper blade.
A what?
A front flipper blade.
Okay, yeah.
Like
yeah.
it looks like the edge is going to be on this side, but the edge is going to be on this side.
Right, yeah, exactly.
It's like, oh,
I see.
wait, I keep getting them mixed up upside down.
Okay, can you explain the foil bag and why it's clean inside and why it looks
Yeah,
good?
okay, so these get cleaned with like dish soap and water, and then they get precision cleaned with acetone and a rag and gloves and everything. And then they're lightly tapped on baby powder, like talcum.
Which is literally Johnson & Johnson.
And then these are special stainless steel heat treat bags that we get made. They're laser welded. And we fold up the open end, the rest are laser welded shut, and it creates an oxygen-free environment where the very small amount of oxygen that's present in the bag gets absorbed, and it will oxidize the surface a little bit, but because there's no holes or anything, nothing more can get in, so it creates like a vacuum seal.
Yeah, you see how suctioned down they are.
If we just left these in the oven loose, they would be like black and
It would look like the outside. but
yeah,
not
it
on
would
the
look
inside.
worse on the outside.
Yeah,
It would be
yeah.
like flaking off. Yeah, so these are always very clean, very almost shiny. This is the one without the engraving.
Cool. Looks good. That's progress, baby. So if you remember what this looked like before, there's one. Morning, Eric. Morning. I mean, look at the before and after difference of the steels.
I got the other one for you too.
They basically go from shiny to dull matte, but and these ones are still oily. You want to wash all that coolant off. And if these blades ever have a little corner that's black or something.
Oh yeah. If there's a burr, it'll poke right through and
Yeah.
it'll pop a hole in the bag.
So we try to deburr them if needed, flat sand them.
Yeah, I've
get
been
any
really
little burrs
gentle
off.
with these
Because they vacuum seal so much that a burr or a bad fold or something
a crease in the bag.
will allow oxygen inside and will, make a corner purple or black or whatever, which is not good for the heat treat of the blade. So when it comes out perfectly clean like this, kind of straw colored, that's good.
They'll get a little darker after temper too. They'll be more straw colored. All right, we've got minutes to get them into the liquid nitrogen.
Sweet.
All right. So these are all going to go in together and sit for an hour in the liquid nitrogen, which, as I've mentioned before, finishes the crystal structure change that we froze when we were quenching them. Also, I've missed a blade, but I'll grab that one in a sec.
I always like the mental visual of red hot, temperature's way up here. We quench it down to ambient,
About room
and then
temperature.
we liquid nitrogen it down to negative 321 degrees.
And
And
then-
that solidifies the crystal structure, right?
Yeah. In a theoretical sense, you want that temperature change from the very top to the very bottom to be as linear, straight line as possible. Some steels are really picky about it. This one's not so much. You've got a little bit of wiggle room, but faster is always better. This is the one I missed. So 2 integral blades, 5 rasks.
So because you're putting a warm blade into a negative 321 degree
Oh, it
Fahrenheit,
is boiling.
it's
Absolutely
boiling the
boiling.
liquid.
If this was full to the top, it would be boiling over.
Yeah,
but
liquid
it's,
would be
it's about
coming out.
halfway right now. I'll start this too.
And we get the liquid nitrogen filled locally about every, 3 weeks still?
3 weeks-ish.
Yeah.
We're tracking it better than we were before.
Nice. Good stuff. Then after that, they go into temper for
2 hours, and then they cool down back to room temperature, and then another 2 hours. And
double temper.
Yep. Second one is kind of a redundancy, but it's better to do it than not to do it.
Yeah. And these ovens they're not 1928 degrees, they're 400 or 500?
Yeah, 450-ish.
Yeah.
All right.
Beautiful. Quick update on the 7075 quench plates that we added, 4 or 5 months ago, last summer?
Summer, yeah.
Yeah.
August.
They're holding up extremely well. I just kind of wiped them with my hand, and this amount of carbon is just from the bags from this run. Like Sky cleaned it and stoned it. We got our Kinetic Precision flat stones meant for aluminum, and I'm feeling it, looking for any high spots or dents or whatever. And there's like where the blades are rubbing right here. There's a texture difference, but not really a flatness difference. They feel really, really, really good.
For what it's worth, this section in the middle just shows how accurate I am with placements when they're quenching.
Exactly. But I lap these flat, and the shininess is still holding up like really well. Good, and then we got a pressure gauge here, which basically shows us, as I'm pushing down on it, you can hold an exact 1,000 pounds or whatever the number is of pressure. They ring together on the way up.
Make sure that this didn't move. Okay. I had it lift out of the peg at the bottom one time.
Yeah, because I've just got it pinned in. Okay, so once the blade has been heat treated, we're still on the fence if we're going to lap it or just surface grind the flats, because lapping, it's a new product, new process. Not quite ready for that yet, we'll see. But then after that, we got to grind the bevels in, and then the blade will come back here for finishing, and Eric, Larry, Gabe, Sky will work with us to finish that blade, polish it up, make it nice, and then work on the rest of the parts.
Oh, baby. Okay. Blades are back from heat treat. Sky did an amazing job. And they have that kind of straw color, that like light yellow kind of color that I was talking about before. They're not so silver shiny anymore. It was funny that Sky, like I've looked at this so much, I know that it goes this way, but Sky kept saying that he thought this was the cutting edge, that it goes like this, but that doesn't make sense. And the tab is kind of confusing here. But yeah, it goes like this. The tab will be cut off in a future operation. Turned out really cool. It's so cool to be able to start to have multiple parts and put them together and start to fit and feel everything as it comes together. I like it. I like it a lot. There are definitely some little features, some fine-tuned details. Like here, we have this double corner round feature where it's double radius. It's not just a top corner radius, it's a bottom. And we actually have this tool custom made that's like this, that, you know, double contours. And we've been doing that since Norseman forever. This is Norseman 200 from 2014, and it has the same double corner radius back there. So try to keep same design logic to future knives. The problem with that is if the tool is slightly too low or slightly too high, or the fixture is weird, or the stock is thicker, or whatever. There's a lot of different ways it can screw up. If it's too low, it's going to undercut, and that is not so ideal. This one actually has that. Can I show it? If you can see, right at the top edge, right there, it has this undercut, which we can fix it to a certain degree. Eric and our finishing team can get in there and deburr it and kind of blend it, but if it's too thick, if it's too much of a step, you just can't fix it. You end up like deburring it too much and having it look dumb. But that's a fine-tuning thing, just happened for the first blade. Next blade come up 1 thou, 2 thou, whatever, and then it should hold really good. So yeah. As I said earlier, the next steps will be to figure out the bevels. They're already designed onto the model. I just have to figure out how to slap this onto the side of the fixture. If I need some custom clamps that are going to hold on to it without exposing the bevel, like while exposing the bevel, so that the clamp can stay in and not be cut by the tools. And then how to cut off the tab. So grind both bevels, cut off the tab, and then from there it goes on to polishing and finishing and tumbling and all that stuff. And then the other big thing I want to do basically now, even almost more important than the bevels, is get the button figured out. So probably our next video is going to be button manufacturing on the Williman, because now that I have parts, yes, I can put them together and go like this, but until it locks up, until I can prove that like the theory is starting to work, starting to come together, because I'm kind of nervous that it's not going to work. I need to prove that out next, because there's going to be some design tweaks. There's no use making 10 blades if the geometry is wrong, if I need to tweak an angle or a clearance or a height or something like that. So button next. It's got to happen next. That's more important than bevels, because bevels is a last thing, is a, you know, that's its own project, has no effect on anything else. The button absolutely does. So yeah, I'm looking forward to making that next. That'll be cool. And then I can actually flip it, lock it up, see if that detent's going to break like I want it to, see if the button's going to drag on this blade like I know it's going to, and how that's going to be. So anyway, super exciting. Progress is good. I love making progress, and thanks for watching. Really appreciate it.